of course, but even the lowest fitness value is still trying to reach to maximum values in both the at both the noise or sigma strength. So now if we are going for another condition where if we are increasing the noise strength to zero point 0.1 and 0.35, then what we are observing is that the fitness value, best fitness or top fitness, of course, try to reach to maximum value, but the lowest fitness value is quite below, and that does not reach to the maximum value. By the way, this 0.25 is basically 0.025, not 0.25. And then we are looking for, so how this we can conclude at the noise strength 0.1, the top and mean fitness value reaches the highest value, that is 0 within 100 generations, while in the previous, what we observe, it reaches the maximum value much earlier with respect to increased sigma value or noise strength. Same results were obtained for 0.35 sigma value. And then what we see here, so one is, by the way, one is basically representing continuous, one is representing a Boolean system. So that is why in some place you could see p value and another is you can see sigma value. So here what I'm saying, left side is continuous, right side is discrete. And that is why in one place I'm using sigma value, in another place I'm using p value, the for the noise. So another condition here, we can clearly see how they are evolving. So in what I'm basically trying to compare, for example, when we have sigma value in continuous model 0.2, so left side, all the systems are continuous system, right side systems are Boolean systems. In most all the like p-values or the Boolean and continuous model, we could clearly observe the similar trend, and thus we were able to establish the synonymous noise strength for both the system, a Boolean and discrete continuous system. And now after analyzing the average fitness over the generations, what we observe here, average fitness in case of left side is basically continuous system, that is ordinary differential equation, right side is Boolean system or discrete system. So here we could see how the uh, average fitness and noise strength plot are basically they look like. I will say it's slightly different in the beginning, uh, both the system, but in general later on the trend is quite similar. Then we went for the average plot, which we can see here, and that is basically adopted from the published paper, from Kaneko's paper. So this is just to show our calculation is purely so our system which we have set up is able to reproduce the outcome similar to what Kaneko has presented in his paper. So what is the difference between his work and my work? The only difference is he was presenting his work for only ordinary system, and I have combined the Boolean system also. So by a Boolean system also, I was fully able to produce the work, reproduce the work, and thus it is quite unique way of presentation. And next, the analysis of evolved networks, how the network behaves. So here we basically aimed to analyze the evolved networks and mainly the network motifs. And as I have mentioned, network motif means the main functional unit of the network. So, network motifs are patterns that reoccur within a network much more often than expected at random. Analysis shows that same network motifs appear again and again in diverse organisms. And the details, if you want to learn more about network motifs, you can read the paper of Milo et al., which was published in Science. Next is the motif signature. So these are well established motif signatures. There are 13 motif signatures. And I tried to calculate the significance of all these 13 motifs in my evolved